All right, so good morning. Welcome to the first ever Legion Bootcamp. Thank you all for coming. So this started when Janine actually suggested that we have a session for her group to learn a little bit about programming in Legion for some work that was going on with one of her projects, and it kind of mushroomed from there with other people who were interested, and we had to move rooms several times, so we wound up in here. This room is, I think it's going to be fine. Just a couple of observations about it. There's no power really in the room, so whatever battery you've got is what you've got for the day. So unless you want to recharge during lunch. The lunch will be out here. We'll be able to eat outside. Looks like the weather's going to cooperate. If you want to use the guest network, you want to just grab the Stanford Visitor, connect to the Stanford Visitor Network, and follow the directions. All the slides are going to be, are already posted actually at legion.stanford.edu. So if you go to our project website, there's a link on the main page to all the slides. So if you want to follow along or see how the slides have changed since last night, you can do that. We're also recording everything today so that we'll be able to put up videos of the talks, and so that'll all be available in the next few days if you want to go back. And we'll just try to capture everything so that we don't have to do this again too soon. Just a couple other details about today. We're going to extend the schedule by 15 minutes. At the very end, at 4:30, we're just going to do Sean's going to do a quick presentation on all the things we're planning to add over the next year. So the coming soon list. And if there are things that you think you would like to see on that list that we don't have on the list, that's one of the things obviously to talk about. I already mentioned the parking. If anybody didn't hear me, if you're not parked kind of in the back towards the left in a place with orange cones that says Legion Bootcamp, then you're in the wrong place and we need to move you. And Sue might be helping some people move, but Sue who has done all the logistics, will be back in a minute and can help anybody with that. Dinner tonight is at P.F. Chang's in the Stanford Shopping Center at 5:30. We'll be done here by 4:45, so there's plenty of time to get over there. Obviously, for people coming from out of town, that's that was something that we could do for you since you're traveling. But also for people who are commuting and don't want to fight the rush hour traffic, if you'd rather stay for dinner, you're welcome to join us. If you haven't RSVP'd about that and want to join us, just let me know or Sue know, so that we can get an accurate count for that. All right, and then just a reminder, tomorrow we're not here. We're over in the Gates building, and Sue has sent out all the information about that. So any questions about logistics? All right. So just a little bit about the project, a couple of slides. So this is the team of people who have been contributing code. And so we have a group here at Stanford and a group also at Los Alamos. Mike recently defected from Stanford to NVIDIA, and so they're now officially. Well, you haven't actually graduated yet. Okay, so that's today, right? We're going to take care of that during breaks today. So we'll be hearing from a lot of these people today, and so you get to know all of these people over the next couple of days, actually. So what is Legion? In case you're in the wrong place, this is a programming model for heterogeneous distributed machines. And by heterogeneous, we mean mixed CPUs and GPUs. We also mean heterogeneity in other ways, but that's the primary form of heterogeneity. And then it's also for machines that are distributed. And here we mean really heterogeneity in terms of memory access. So you have a very large spread of different memory devices that have different speeds and a lot of variability in the communication latencies. And just as a history, this project started in 2011. We had the first version out in 2012, but then in 2013 we decided to do a big application. We were working with Jackie Chen's group at Sandia on porting S3D, which is her group's major code, to Legion and then running it on the national resource supercomputers. And that work is actually ongoing as part of the Exact Center, funded by DOE, and has driven many of the changes and additions of features to the model, and also a huge amount of optimization and improvement in the underlying code base. And currently, we're scaling that up. It's currently running on Titan, so this is our flagship application. So just to give you, this is a scaling plot showing throughput per node as we scale up the number of nodes down here from just a few to 8,000. And then this is various configurations of both the software running different problem sizes and on different machines. And the red lines here are the OpenACC version of S3D. And you can see that the Legion version is doing quite well. And generally, we're like 2 to 3 times faster than the current production version of S3D. So this is where, you know, the application where we've invested a lot of time. There's a bunch of other things, and we'll be hearing more about this today. I'd be happy to talk to anybody if you want details of what it's like to try to do this. There's a lot of scars on the back in getting that to work. Now, the Bootcamp focus today is going to be on communicating to you how we write Legion programs. And this is going to be different from the academic papers. There's a bunch of papers on our website. But we're going to try to convey a different kind of information here. We're going to, you know, covering mostly pragmatic and usability aspects. We're trying to emphasize those. So this morning we're going to talk about the programming model, and the important things are tasks, regions, and the mapping interface. And then this afternoon we're going to talk about everything else. Just, you know, little anecdotes about how we structure applications, some of our experience, our debugging and profiling tools, and, you know, all the other stuff you need in order to actually write applications. And then tomorrow we're going to work with the application groups individually. For those of you I didn't postpone to another day so that we could deal with the groups who are coming from out of town. And if you think you're in a group that's meeting with us tomorrow, I'd like just to connect with you today, because I have my count of how many groups we have, and I just want to make sure that's actually consonant with how many people, you know, think they have an application that they want to talk to us about tomorrow, so we can not be too surprised in the morning. All right, so but that, and again, that's going to be in the Gates building, which is on the other side of campus tomorrow. All right, now, getting started. So part of the philosophy of the project, and this is maybe a little bit of advertising, is that, you know, from the beginning we wanted this to be a real programming system. So I've been involved in many academic research projects and programming languages, and I actually use the academic word. I don't mean academic to be a pejorative. For me, that's a positive adjective. But we wanted this to be, you know, a little bit more in the sense that we were going to invest the time to make it into a real system. It's going to be beyond, you know, it would work on more than the examples that were in the paper. And so we spent quite a bit of time, you know, designing what I consider to be a good programming model, and that it has good abstractions and a clear semantics, so you can actually reason about how things are supposed to behave when you write the code. But also, it's designed so that you can open the hood and get down to lower levels of abstraction below the advertised layer if you need to make things work. Okay, so there are various ways in Legion to kind of open up the hood and fiddle directly with the important pieces so that you can make things go fast, essentially. And of course, these lower levels of abstraction, they're more complicated. Cognitively, there's more you have to know in order to do that. But the good news is that you can do it within the programming model. So still, most of your code is in the higher level abstraction, and then there are places where you can, you know, in limited ways and with limited scope, affect things by, you know, by opening up the hood and getting in and working at a lower level. All right, and we'll talk some about that today. We'll see some examples of that. Now, let me just show you some example code. So here's a screenshot from one of our papers. I think this is our very first paper. This is how you do a little circuit simulation, and this example will be mentioned many times today. So it says 3 loops, and you have you have an outer loop which is doing time steps, and then 3 loops which loop over a chunked up graph or a mesh, and you're just, you know, doing 3 operations on each of those pieces. Okay. And here's the actual code out of the repository. And I was actually pleased to see that it looks pretty much the same. So this is a few years later, and the code doesn't look that different. And so you can actually see the, you know, the relationship between these two. But this brings up our first point. You know, so where, if you look at this, you know, where is the parallelism in any of this? And it actually, if you're a programmer in Legion and you're writing to the programming model, you're writing something that looks like a sequential program. Okay, so it has a sequential semantics. And that makes it relatively easy to reason about. You can, you know what the thing is supposed to do, and the implementation promises to be faithful to that sequential semantics. Again, there are some advanced features where you can get past that. Huh?
You want to speak on it and ask questions?
Yes, I should have said that. Yeah.
Okay, so when you put this up, I the same thought you just said. And I look at this and I see the, like the sequential order. But knowing that I'm spawning tasks, how is the runtime going to figure out the ordering of those tasks?
Yeah, so the runtime, we're going to come to this. The runtime is going to be analyzing the dependencies between the tasks. So you're going to tell the runtime enough information about what each task is doing that it can, online, at runtime, analyze dependencies between the tasks and extract the parallelism that way.
So
Okay.
you go through how dependencies are expressed?
Huh?
You'll go through how
Yes, yeah. So I'm going to do here in the remaining 30 minutes I've got is to give you an overview of the whole thing. And then we're going to do it again more slowly in the subsequent several talks. All right. So I'm going to try to get all the terminology out in this talk. All right. So it has a sequential semantics, which makes it easy to reason about. But again, you'll see this afternoon that there are some ways to go beyond that. But the main point on this slide is that this is not like MPI, OpenACC, or CUDA, if you're familiar with programming in one of those. You can't bring your ideas about how you program in those systems to Legion and have a good transition experience. Okay, so you need to you do need to kind of wipe the slate clean and think about this as best you can with fresh eyes. Is there another question? Yeah.
Real quick, when you say when it runs on GPUs,
Yeah.
each task is assigned to a warp or whatever GPU, correct?
So we don't have that kind of level of scheduling on GPUs. I mean, that's not exposed to us. If it was, we would definitely take advantage of it. But currently, it's just a kernel launch on the GPU is the unit of task. So you're running on the whole GPU. So
you still need to have thread parallel. It's not sequential in that sense.
Yes, well, so Legion is agnostic to what your leaf tasks are.
Okay.
So Legion doesn't care what the leaf tasks are. They can be anything.
Okay.
All right, and it's a way of piecing together your kernels, if you like to think about it that
So
way.
in that way, it is like CUDA.
In that way, it's a little more, that way you can think of it a little bit like CUDA. I mean, it wraps CUDA, because we don't have a finer level of scheduling granularity on GPUs at the moment. Okay, in the future, I hope we will. Yeah. All right. Okay, another point to emphasize, the second point, is that this is a programming model. Okay, it's not a programming language, but we'll talk about the efforts towards actually having a language level implementation of Legion later on. The main implementation is currently embedded in C++. Okay, that's not going to change. I mean, it's a C++ runtime library. All right, and so all the usual C++ isms and you can use all of C++, and then you just have this API, literally a bunch of runtime functions that you can call that implement Legion semantics. Now there are a bunch of restrictions on how you use those, and that's why having a language might be nice because then you have something to actually check those restrictions. But we're going to tell you what those restrictions are. Okay, so yeah, so you can use all your favorite C++ constructs in writing Legion programs. Now, since it is a runtime system, that means all the decisions are made dynamically. So all the decisions about what's going to run in parallel, where things are going to be scheduled, everything is done at runtime. And this is actually a conscious design decision on our part. We actually think that's a good thing, not a disadvantage. Because we are able to take advantage of all the runtime information to make better decisions. Okay, and the issue then, if you're familiar with dynamic systems, runtime systems, is that there's going to be some overhead. For every task launch that you do, for every unit of work, of useful work that you do, you're going to have some runtime system overhead and decision making about how that's going to get executed. So we're not going to go into the details today of all the optimizations that we do to keep those overheads down. But it's at the point where if you write tasks with reasonable granularity, and we can talk about that at some point today, then you will not see a lot of overhead. Okay, and we don't see a lot of overhead in the well-tuned applications that we write. Now, so what is a task? I've already used the term a few times. I haven't told you what it is. It is the unit of parallel computation in Legion. All right, so you can think of it as a function call that is potentially going to execute in parallel. There are two interesting things that are important to know about tasks. One is they take special arguments called regions which are typed collections as arguments, and the region is a Legion data type, and Legion knows an awful lot about regions, as we'll see. And the other thing is that tasks can launch subtasks. So tasks can recursively launch they can decompose themselves into smaller units of computation, which may also run in parallel. All right, so now in this slide, let's see here. So in this slide, we have some interesting things about tasks. First of all, let me just point out this call here is actually, this is actually a launch of multiple tasks simultaneously. So this is one of the ways of reducing the overhead. If you have a vector of tasks or something like that, you're going to map over some regular structure. We have a particular way of launching tasks that you should use for doing that, called an index-based launch. Okay, so if you're going to launch, like if you have a mesh that's divided up into n pieces, and you're going to launch one task per piece, this is the way to do it because it'll have lower overhead than launching individual tasks for each of the pieces. Okay, so that's what the purpose of the index-based launch is. And then what does a task take? Well, it takes this thing called a context. That's the first argument. That's information about its parent task. So every Legion task executes in the context of a parent task. All right, and the context is managed by Legion. You don't mess with that, but you have to pass it on to the child tasks so that Legion can hook up who's a child of whom and do the things it needs to do. You need to pass in a task ID. So this is just a global constant that names the task, the particular piece of code that's going to be run. That implies that somewhere, and indeed you need to do this, there's a registration procedure when you start up to register all your tasks with the Legion runtime. So you're going to have a list of kernels that you want to run, and they're all going to get registered. They'll all get assigned one of these constants, and then you use these when you want to launch the tasks. And then the region arguments and what we call the region requirements are also passed in to each task. This names the regions that the task is going to use, and also it tells a lot of information about how those regions are going to be used, which is we use for inferring parallelism. Okay. And then you can pass, I forgot to say, yeah, and then since this is an index-based launch, you need to say something about how each of these tasks is different from each other. So the task space is just a way of naming all the individual tasks, how many you're going to have, for example. And then the local argument says for each of those tasks what's different about them. What special piece of local state do they get that the other tasks don't get, okay, out of these multiple tasks that you're launching. Okay, so the per task information that's different, it goes in the local arguments. The task space names all the different tasks. So what do you wind up with when you run a Legion program? You wind up with this tree of tasks. So you have one task at the root, which is the initial main task that starts up, and it can launch subtasks, and those can also launch their own subtasks. So Legion programs can launch an arbitrary tree of tasks, and by default, they're executed in the order launch. They're executed in regular sequential order, and then the runtime system is automatically going to identify parallelism. So now let's talk a little bit about regions, because this is the part that is really most central, maybe in a way, to the Legion programming model. Certainly has the most to learn for a programmer. Okay, so this is the part that's probably has the most new things relative to, or different concepts relative to other programming models. So the first thing is that regions are defined using index and field spaces. Okay. So an index space just is a list of points in an n-dimensional space. All right. So you can think of it as the rows of an array. If you have a three-dimensional array, it might be a three-dimensional object. All right. But it's just a list of points. Okay, a set of points, I should say. And then a field space is a bunch of fields that you want to associate with a particular. Well, it just names a bunch of fields. So for example, if you have pressure, temperature, and acceleration as three values that you want to associate with lots of different things, those would be three different fields. You can think of them as the fields of an object. That's why we call them fields. Okay, but our field spaces are defined separately. You can just say, I'm going to have these three fields that I want to have be together, so they could be in a field space. And again, these are allocated dynamically. So the index spaces and the field spaces, you create these at runtime, and you can add and remove elements of field spaces and index spaces as you execute. So everything can be altered dynamically. And then a region is defined as the cross product of an index space and a field space. Okay? And that gives you a table. So in this case, we have a bunch of, we're defining the nodes of our circuit simulation, and we're not going to have an interesting set of fields for this, in the actual implementation. We just have a one-dimensional table. So it's just a set of nodes. Okay, so we have n nodes. The only thing that goes in a node is a node itself. We're not subdividing into any of the other fields that we might be interesting, at least from the point of view of what Legion knows about. And you wind up with this hard-to-see one-dimensional table on the right. Okay, so regions consist of two dimensions. You have an unbounded set of rows, all right? And you have some sort of named set of columns, okay? And those are the fields, all right? And so so everything in Legion, regions always name these tables. And you can think, if you're a database person, you can think of them as relations. If you're an object-oriented programmer, you can think of these as sets of objects, okay? They're just collections of objects. Every region is typed, meaning that it has to have, you can't mix different kinds of elements within a region. So every region is one of these tables, all right? If you want to have different fields, different sets of fields, you have to have a different region for that, okay? And I guess the only other thing that I would point out, oh, and if you're a Fortran programmer, you can just think of these as arrays. Okay, that's the other thing, yeah.
So you said that one region has one set of X and Y in this
Yeah.
table, essentially. So if you have edge and face and stuff, then those would all be different regions.
Well, it depends how you want to do your application, but yeah, normally you would have a region of edges, a region of faces. That would be one way. That would be a logical way to do it. Okay. Now, so what are you going to do with regions? So tasters are going to declare what fields they use out of regions. Okay, so tasters, first of all, they're going to declare, I should have put this on the slide, they're going to declare what regions they use. Then they're going to say what fields they use within those regions. And then they're going to say how they use those fields. And that's what the information that's going to be used to infer parallelism. The Legion runtime is going to compare different tasks, say, oh, if they're working on different regions, they can run in parallel. If they're working on different fields within the same region, they can run in parallel. If they're working on the same field in the same region, but they're just reading, for example, they can run in parallel. And there's a lot of different ways that it can prove that it's okay to overlap tasks. So doing a good job describing which regions you're using and what fields you're using is important. Okay, and being precise about how you use them is also important. The other thing you can do with regions is partition them. Okay, so partitioning works in the following way. So this is actually just some code, and I think it's probably readable. If not, I'll just talk through it. So what we're going to do here, here's our circuit. This is an electrical circuit. Okay, it's just a bunch of wires that that are connected at nodes. And we're going to ultimately build a circuit. We're going to build a data structure that partitions this circuit into three pieces. Okay, for the purposes of doing some calculation in parallel over the three pieces. But the way we're going to do this partitioning is actually a little bit non-obvious. So I'm going to walk through this, and this is what our actual implementation does. So N here is the region of all nodes. Okay, we start out with one big region of all the nodes. And the first level of partitioning is to divide it into the nodes that are private to a piece and shared between pieces. So we're going to look at the graph in the following way. There are nodes in blue that are not connected by an edge to a node in a different piece. They're only connected to nodes within the same piece. Okay, and then the nodes that are colored in red, those are actually on the boundary between one piece and another piece. Okay, so the first partitioning is going to be between these private nodes and these shared nodes. And so it's just a global partitioning of the blue set and the red set. And then we're going to do a second level of partitioning. Regions can be partitioned recursively. Okay, to divide up the private nodes into into a bunch of different subregions, one for each piece of the graph. So in this case, there would be three different private subregions, one for each subpiece. Okay, and this is partitioning the region of private nodes. Okay, and what's going on up there is we create a partition object, and then we actually do the partitioning and get a subregion back. All right. And then the shared nodes, the global set of all the shared nodes, are going to be partitioned in two different ways. Yeah. Yeah. Sorry.
Is this generally meant for like communicating across nodes with MPI, or is it more general than that? It's more general than that.
Yeah, I think it's more general than that. We're not,
But you
So-
can use it to do that. Okay.
yeah. So yeah, I don't want to say don't think about MPI, okay? But that's probably what I should say. You know, this is the simplest thing. Just like for the moment, just accept that we want to do this, and you'll see how it gets used, you know, in a minute. All right, so we're gonna, yeah.
And it's fair to say that what we're doing here is similar to the MPI ghost cell. approach.
Yeah.
I mean, the terminology is very similar.
Yeah, that's right, that's right. No, this is good. What's probably a little bit unusual is having this top level of partitioning into the private and shared first, and then doing this lower level. All right, so then we would break all the shared pieces up, all the shared nodes up into the different pieces that are shared, the different shared nodes for each piece, okay, the different sets of shared nodes for each piece. But then we're also going to do another partitioning of the shared nodes, which is the ghost nodes. Okay, and the ghost nodes are the nodes that are on the boundary of that are in another piece, but on the boundary of your piece. So, for example, the ghost nodes for that piece in the upper left-hand corner are the 4 nodes in green. Okay, and that's a different view onto the shared nodes. So every piece has its own set of ghost nodes, and those actually are interesting because they can overlap. The ghost nodes of different pieces here will actually not be disjoint. All right. So, for example, this node is in the ghost set of this piece, but also in the ghost set of that piece. All right. And that's indicated in this partitioning tree by the hollow rectangle there above the ghost node. So if a partition is disjoint, we usually color it solid, and if it might be overlapping, so the sub-regions might not be distinct from each other, then we leave it open. Okay? And so this is the data structure then that Legion will use to help it infer what can be run in parallel and what can't. Yeah.
Sorry, maybe follow up to that question. So the distinction between the two types, is it more where the data resides in terms of nodes? Is it a read versus write distinction?
I couldn't understand you. I'm sorry.
So the reason you partition into shared and goes, is that based on where the data resides or across nodes, or is that more of a read versus write distinction?
Yeah.
At any given time?
So I'm not going to answer your question directly. So the one thing is we don't think yet at this stage about where the data resides at all. Okay? So that's a decision that's made later. And now we thought about that in mapping. So mapping is separated from the specification of the program. And when you write in Legion, you know, when I showed you that little bit of Legion code, there was no discussion there of what processor things were running on or where any of the data was stored. So those decisions are factored out into a separate mapping phase. And yes, we will have to say for each of these subregions where it is going to live. But actually the runtime system can have multiple copies. We can, you know, if it's safe to do so, the runtime system, and you can map it this way, will have multiple copies, say, of the ghost nodes, or the shared nodes, whatever you want, in the system, and it will maintain the coherence of those copies for you. Okay, so the logical regions, i.e. Legion, you know, is a level distinct from what goes on underneath, which is one of the things where you can get down and control the performance, which is the mapping level, okay, which are the physical regions. All right.
Can I take a crack at answering the actual question?
Go ahead. Yeah.
So you know, the reason that we have this more complicated partitioning is it gives you a more precise information about how your data is actually divided, and that's going to allow the runtime to infer better, you know, where task parallelism exists. And so, you know, this is a more accurate representation. Normally, you know, right now when you write an MPI code with ghost cells and stuff, you know, I think it's okay. You know, you tend to partition things to talk about ghost cells and your own cells and stuff, and that's fine. But it's very explicit. You have to manage all the dependencies yourself. Whereas this more accurately captures the logical partitioning that, you know, is good for describing tasks and how they're actually going to use data.
So you built the graph in terms of the Legion, obviously. So you have some graph representation.
Yeah, so the graph is going to be represented in logical regions, right? And you're going to, you know, the process of computing that partition, like computing into pieces, is done by something like Parmenas. And then what we're going to do is capture the result of that partitioning using these logical regions and subregions of partition. So,
But you have your own graph representation. Is that on the actual degree of freedom level, or is that on a region level?
I mean, you can put whatever you want in logical regions, right? So,
No, you could have the graph be whatever you want it to be.
yeah.
Can I ask one more question on this?
Sure.
So it seems like you made an assumption here that nodes interact only with near, so those are locality assumptions. What about if there isn't that locality in the problem?
Well, so yes, one of the key things, and I'm going to probably not answer the question again. one of the key things in Legion is design decisions is how you break things up into regions. And one of the things you use regions for is to capture locality, to express locality to the system. To say, things that belong in a region together are things you plan to use
I'm
together.
not worried about that part of the problem,
Yeah.
more the physics part of the problem. So suppose you had, how would you capture locality in this context? If you had a node that interacted with, dozens or hundreds of other nodes in the system, or even all the nodes for that matter.
Yeah, so you have to, that's part of your problem as a programmer, to figure out how to structure things so you have decent locality. What's going to happen is if things wind up, if tasks wind up on different nodes, say, and they require the same regions, then the system is going to insert communication to move the data from one to the other according to the original issue order of the tasks. So when one of them is done, it'll move the data across to the other. It'll make sure that every task gets the regions it needs in the correct version that they need. And then it's up to you as a programmer to do a good job of partitioning tasks in regions and doing a good job of mapping these onto the
Have
hard
you guys
disk.
done any problems like that? Example problems?
Method of moments codes. That's a good example of what you said.
Okay.
Are these like very graphs with small updates and stuff? And so big distributed graph problems are one of the few things that we don't do very, very well. Okay, we can do them, but if you don't have any locality, we can't help you, right? Like that's an inherent problem of your problem that you're working on, and we're not going to do anything
You
magic
do
to
things
solve it.
like fast multiple in order to create locality.
So I can talk offline with you about fast multipole. We have done some work on that. But if you have a big distributed graph and you're doing random reads and writes to arbitrary nodes in that graph, we're not going to do anything to help you.
All right. Can I toss out a slightly different take on it? The same thing is that one of the key things you can do with partitions and regions in Legion is they're dynamic. So you may have an application which over the entire lifetime has basically no locality. Every node is talking to every other node. But you might have portions of it, either in time or space, where, for the next some amount of time, I'm talking mostly to these nodes. And you can stop and you can build a partitioning at that time to describe what your access pattern is going to be for the next couple seconds. And then the runtime can take advantage of that. And then when you're done with that, you can tear it down and go make a new partitioning for the new way things are set up. And so you don't have to set up everything at the start and have one fixed way of doing things. You can actually adapt to different access patterns in your data, or possibly that, if you're doing particles, maybe the data itself is actually moving around. But, if it's truly random access, then you've got a different problem. But to the extent that there's any non-randomness in it, this
There
gives you
are
a way.
physical problems that have that.
Yes.
Yeah. Okay, so I'm going to abbreviate my talk a little bit because I don't want us to get behind right at the beginning. So I'm just going to skip ahead. So I was going to say a little bit about how you populate regions, but there's various ways to get to get data into regions. Let me skip over that. Okay, so just a few words about privileges and coherence. So I've already said your regions tasks need to declare how they use their regions. And so there's a bunch of different modes in which tasks are allowed to access regions, and these are some of them. So we have these things called region requirements that you need to build, and essentially if you were writing in a programming language, it might look like that, where you have these declarations saying I want read and write privileges, and I want to be the only one touching, I want exclusive access to my private wires piece, of my graph, that's RW_private, and I only need read-only access, ROE, read-only but exclusive access to the node sections, so the private nodes, the shared nodes, and the ghost nodes for my piece. Okay? In C++, it looks like this. It's a bunch of calls to the API, one for each of the different requirements on each of the different regions. And you build up this data structure with all these, and this gets passed in as part of a task call, saying these are the regions I'm going to use, and this is how I'm going to use them. All right. Okay. So now, so just here, this is the code I showed you at the beginning. So just coming back to this, this task space and local arguments. So again, this is an index launch, meaning we're launching one task here per piece in this case of the graph. So the task space is just names all the different pieces, saying I'm going to run if I have n pieces, I'm going to run n tasks. The local arguments is just a vector of those pieces, saying here's the piece at each task is going to get for this launch. And then the region, the CNC underbar region piece, that is the region requirements, saying which tasks, which regions they're using, and how they're going to use them.
Question.
Yeah.
The output regions that you're writing to, do they have to be pre-allocated perfectly, or can you add to them while you're running?
You can add to them while you're running. Yeah, so you can allocate space in regions while you're running. Yeah. Yeah. And okay, so now just to summarize this first talk. So the crucial design decisions in Legion programs. And this, if you remember, only one thing from this presentation. So what are your regions going to be? So how are you going to divide up your data? Okay. And what are going to be the tasks? And in particular, it's not just the regions and the tasks, but how you're going to subdivide each of those things. So how do you divide the tasks into subtasks? How do you partition the regions into subregions? And often there's going to be a tension between the two things. Okay, so this is the hard part. And also, these are the decisions you make first in Legion programs, and the ones that become, they're not impossible to change down the road, but these are the ones that are harder to change. Okay, so these are the things that are important to get right. And so tomorrow, I expect when we talk to people in the application groups who are starting projects, this will be what we'll focus on. What's the best strategy for partitioning tasks and data so that you have the most flexibility as possible as you go forward, trying to get something that's going to run well.
So, just so I understand that right, so what about if I have a code that say like something like a discrete event simulation or some other things that we can do where literally I just kind of compute an output, normally an API would just send that to some other task. Does it mean in the region model I would essentially just make a region that is just specific to that one quote unquote message, and then the next guy would say, well, I input the same region, and then that would essentially encapsulate.
That would be one way to encapsulate the dependency. Typically, you really have a set of those things. Each one's producing one.
Yes.
Right.
Yeah.
Right.
Okay,
so you might have a region and some subregions that would capture, whatever the data is. Now, if you only have one thing, if you literally have one value that you're producing, then we have another way, to help you with that. Okay. So the regions are really for collections. Okay. But we also have a system of futures, so that you can pass around in the system. All right. But what you said is completely correct.
You don't have promises though, right?
Huh?
You don't have promises?
We don't have anything called promises.
Okay.
Right.
Is there something that fulfills that?
I don't even know what a promise is.
Okay. A promise is,
Yeah, so probably not. That
Okay.
might be right.
you know you're being recorded.
Okay. One word about mapping. So now, after you designed your program and you have your regions and your tasks, and then you have to decide how you're going to map it onto the machine. Which processors the tasks are going to run on, what memories the data, the regions will live in. And this is the part everybody wants to talk about, usually, because it's, I guess, the thing that makes everything very concrete. Okay, so you're going to have some mapping from tasks onto processors and from the regions and subregions into various memories. The mapping, I'd just say, is computed dynamically, and it's designed to decouple correctness from performance. So you get your code, and we actually write our codes this way. We get them working first in a low performance way in the structure that we want. We make sure we have all the correctness, and then we start going in and tuning with the mapper. All right, trying to get performance out. And we actually develop that way. We recommend that everybody else develop that way. So don't, it's a way of staging things that works well. Okay. The mapper interface is a bunch of callbacks that the runtime system makes to your code. So you write a bunch of callback routines, and when the mapper needs to, when the runtime system needs to place a task somewhere, it'll call your callback for mapping a task and say, where do you want to put this task? Right, for example. All right. So, okay. So again, the crucial things are, what are the regions, what are the tasks, and in particular, the mapping decisions are going to depend on the design that you got for the regions and the tasks at the beginning, not the other way around. Okay. So first, you have to get the regions and tasks right, and that gives you the space of possible mapping decisions you can make. And then we have some debugging tools that you'll hear about this afternoon. We have some cool performance graphs that we might get to see again. And I already took a bunch of questions, and I should stop because we're a couple of minutes past. But if while we're making the transition, I'd be happy to answer any high-level questions or even and avoid low-level questions. Yeah.
Where do I find the slides on?
Should be at the legion.stanford.edu. So that's our project homepage. And then on the page, there should be a link that is a pretty prominent link.
Yes, it's right at the top of the